We'll be performing a multivariate linear regression using Microsoft Excel. So we're going to use the data set I have pulled up here. The data set is linked in the description below. It comes from Jeff Wooldridge's Introductory Econometrics textbook, which is also linked below. Okay, so the data we have is data on a housing market. Okay, so each individual row corresponds to a single observation. So the unit of observation here is a single community. So we have information on what we call price, which is the median price of a home that was sold in that community. We have information on the crime rate in percentage terms in that community. We have information on nitrous oxides. Here we call it NOx, which is the local concentration of nitrous oxide emissions in parts per million for that community. We have information on rooms. This is the average number of rooms in a home in that community. It may look a little high, so this doesn't count just bedrooms, but total rooms in a home. And then finally, we have information on property tax of that community. So this is, again, in percentage terms, what is the property tax, the average property tax for that community. Okay, so with this data, we can run a lot of different models. So what we're going to start with in this video is just a multivariate linear regression. And specifically, what we want is to run the following model. So we want to model the price of a home in community I as a function of the crime rate in that community, the nitrous oxide emissions or ambient pollution in that community, number of rooms, the average number of rooms in a home in that community, and then that community's property tax. Okay. Now we'll just run that regression. We'll build that same model in Excel and look at the output. Okay. So to run this regression, what we need to do is go to the Data tab up top and go all the way over to Data Analysis. Click that button, and there's a lot of tools available here, but we're going to focus on regression for now. Hit OK. Now it's going to ask us for the Y range and the X range. So the Y range is just what is the Y variable? What is the dependent variable? In this case, for our model, that's going to be just price. So we're going to select the entire column for price. Okay. And for the X range, we are going to select all of the X variables. In our model, that's crime and nitrous oxide and rooms and property tax. So we're going to select all four of these columns together all at once. And it's important when we're selecting these things to include the first row. So that first row provides us information on the names of the variables. So if we include that when we're selecting the data and then hit this labels option, that's telling Excel to ignore the values here because they're just words. But then when Excel provides us the output, it's going to label the output with these labels so that we can understand. Otherwise, we may get totally lost at trying to read the output table. Okay, so when we're selecting the ranges, both Y and X, include this first row of labels and then click the labels option. Okay, and then finally, I'm going to send the output of the regression to a new sheet. That's the default option. If you'd like, you can also choose to put the output inside the same sheet. For now, I'm just going to keep it as in a new sheet. Okay, that's all we have to do. We hit OK, and Excel will run the regression. Okay, and there it is. It has been moved to a new sheet called Sheet 1. So I'll zoom in here so we can look at some of the output. Oop, a little far. Okay, so the first thing we want to look at is the regression statistics. So we have the R squared and the adjusted R squared. In this case, we're running a multivariate regression, so we want to look at the adjusted R-squared. The adjusted R-squared here is 0.57, which means that our explanatory variables are explaining 57% of the variation in the price of a home. Okay, not too bad, right? The adjusted R-squared will range from 0 to 1. 0 is typically bad, 1 is typically very good, or at least as close as you can get to 1. And so an adjusted R-squared of 0.57 is fine. There's no red flags here. Okay. So next we want to look at the F-test. So the F-test here is testing whether the model is jointly significant. So the null hypothesis here is that all of the slope parameters are these things here, are equal to 0. Okay, and then the alternative hypothesis for the F-test is that at least one of them is significant. Okay, so if we look at this cell here, this gives us the p-value associated with the F-test, which is a very small number. And if we compare that to our alpha of 0.05, we very easily reject the null hypothesis. Okay, so what that means is that at least one of our slope parameters, one of these four coefficients here, is significant. Okay, before even looking at this kind of bottom table here, this result tells us there's at least one variable in our model that's significant. Okay, so that's important. Our model isn't totally useless, right? Okay, so then the last thing to do is to actually look at this this bottom output table. So what this is going to give us is the actual coefficient estimate, the standard error of that estimate, the t-statistic, which in a regression framework is just the coefficient divided by the standard error, and then the p-value associated with the t-test. Okay, so there's a t-test that's associated with each of these coefficients, and that t-test null is that the coefficient is equal to 0, and the alternative hypothesis is that it's not equal to 0, at least the way we're approaching it here with the two-tailed t-test. Okay, so let's just look at this intercept here. This p-value is significant. It's much less than 0.05, which is our alpha, our significance level. So we reject the null. When we reject the null for the t-test, that means that we have a significantly different from 0 coefficient, which means this coefficient is significantly different from 0. Or just simply, it's significant. Okay. So this first coefficient here is significant. This second coefficient, this is the coefficient on crime, is also significant. This third coefficient on nitrous oxide is also significant. This fourth one on rooms, also significant. And finally, this last one on property tax is also significant. So as it turns out, the regression that we've just run, all of the coefficients, even including the intercept, is they're all significant. Okay, and that's all just based on our alpha of 0.05. If we change our alpha around, we may have to change our decision, but typically alpha is set at 0.05. So given that, we can say that all these coefficients are significant. Okay, so quickly then, how do we interpret these? So this is just a linear regression, meaning that the interpretation of the coefficients is just unit to unit. So let's focus on rooms for a moment, okay? So the outcome variable, if we switch back to our model, is price. And price is measured in dollars, okay? Just US dollars. And rooms is measured in rooms, right? A single room is a single room, 2 rooms is 2 rooms, etc. So beta 3 is the partial effect of rooms on the housing price, right? And so the way we're going to interpret that is a unit change in rooms is associated with a beta 3 unit change in the price, which sounds very robotic, right? That's not necessarily a smooth way to say that. So instead, what we're going to say is that an increase by one room is associated with a $7,700, almost $7,800 increase in the price of a home. Okay, which means that as a home increases its number of rooms by one, so let's say you have a house, you expand it by one room, that should add about $7,800 to the price of your home. Okay, positive, just like we expected, and the interpretation there is pretty straightforward. Next, looking at NOx. Again, NOx is measured in parts per million. So a increase in nitrous oxide concentrations by 1 part per million is associated with a $660 decrease in the price of a home. Okay. Looking at crime, an increase in the crime rate by 1% is associated with a $136 decrease in the price of a home. Okay. And the reason I use percent there is because crime, as in our data set, is measured in percentage terms. Okay. So when we look at the raw data, crime is given to us in percentage terms, so the unit here is a percent. Property tax is a similar situation. So what this is saying is, as the property tax of a home increases by 1 unit, which in this case is 1%, then the price of a home should drop by about $90, $89. Okay, so there we go. We've run a multivariate linear regression. We get the results. We look at the model fit, and we can interpret the coefficients.